Okay, so quick look at the schedule. Today is Halloween, October 31st, 10.2, right on schedule. I'm not opening anything up today, and that goes for the rest of the week. Nothing else new will be opened up, with the exception of the homework, which will be updated on Alex. Okay, just keep in mind that the Chapter 10 homework is due on November 28th. That seems like a ways off, but this semester is going very quick.
In the Panama Papers and secretly controlling.
All right, so here we go, ladies and gentlemen, section 10.2. The fundamental counting principle and permutations. Okay. All right, by the time we get done with section 10.2, we will know how to employ the fundamental counting principle, calculate the value of a factorial function, find the number of permutations of n objects, find the number of permutations of n objects taken r at a time, and find the number of permutations when some objects are alike or repeats of each other. Okay. All right, now in a sequence of n procedures, if the first procedure can occur in k sub 1 ways, the second procedure can occur in k sub 2 ways, the third procedure can occur in k sub 3 different ways, and so on. The total number of ways the sequence of procedures can occur is the product of these individual number of ways. This is called the fundamental counting principle, okay? And it enables us to determine the number of ways that different things can occur in a particular sequence. Okay, for instance, here's an example. There are 4 basic types of blood represented by the letters of type A, type B, type AB, or type O blood. But you also have a Rh factor attached to the blood, which is either positive or negative. If a local blood bank labels donations according to the type, the Rh factor, and the sex of the donor, how many different ways can the blood sample be labeled? Well, ladies and gentlemen, notice for the blood type, there are 4 different types of blood. So there's 4 different ways in which the blood types can occur, times there are 2 different types of Rh factor, either positive or negative. So we multiply it by 2, times there are 2 different sex, male and female, times 2. Now, from the fundamental principle of counting, therefore, there are 4 times 2, which is 8 times 2, or 16 different types of blood vials that can be labeled. Okay. Now, another way of enumerating all, notice they did not want us to enumerate all the 16 different ways. They just wanted us to determine how many different ways blood samples can be arranged here. If you wanted to enumerate the number of different ways, you probably would want to use what's called a tree structure to help you do that. For instance, let me kind of show you how you could build a tree. The first branch is going to be the blood type. So we're going to have 4 main branches here. Where you can have type A blood, type B blood, type AB blood, and type O blood. And then from each type of blood, you can have 2 branches coming out, which gives you an Rh. This is your Rh, positive or negative. Likewise, positive or negative, positive or negative, positive or negative. And then from there, you can have 2 more branches coming out, which gives you the gender, male, female, 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 male, female. All right, and then by following the branches of this tree, you can enumerate all 16 possibilities. For instance, you could have a type O blood with an Rh positive factor, and the person could be a male. So you could have A plus male. You could have type A blood, positive Rh factor, and a female, A positive female. You could have type A blood, negative Rh factor in male. So A negative male, A negative female. You could have type B blood, positive and male. Type B blood, positive and female. You could have type B blood, negative Rh factor and male, B negative male, or B negative female. Or you could have type AB blood, positive male, AB positive male, or AB negative negative, wait a minute, positive female, excuse me. Or you could have AB negative male, or AB negative female. Or you could have type O blood, positive Rh factor in male, or type O blood, positive Rh factor in female. Or you could have type O blood, negative Rh factor male, and type O blood, negative Rh factor in female. And ladies and gentlemen, there's your 16 possibilities or arrangements. Everybody see what I just did there? How to enumerate all 16 possible arrangements here. All right. Now, you could see where this could get out of hand very quickly, though. This was just 16 possible arrangements, okay, different arrangements here. Could you imagine if you had like maybe 720 different arrangements for something? Try drawing a tree structure for that. That would not even fit on your paper, and that would be extremely difficult, virtually impossible to draw on a paper. Okay, so this was a nice problem to be able to visually show you how to enumerate all the possible arrangements here. All right. So the fundamental principle of counting enabled us to determine the 16, the fact that there would be 16 different types of blood arrangements there. Here's another one. The letters A, B, C, and D, and E are to be used in a 4-letter ID card. How many different cards are possible if letters are allowed to be repeated? Okay. Well, how many letters do we have to choose from? We have 1, 2, 3, 4, 5 letters to choose from. And yet our ID card is to only have, what, 4 letters. And notice the requirement is that the letters can be repeated. So A, B, C, D, E. Think of it as being 4 mailbox slots. How many different ways can I populate the first mailbox slot? How many different letters can go in this slot? How many?
4.
5. There's 5 letters, correct? We can pick from any one of these 5. There's 5 ways of populating the first mailbox slot. But ladies and gentlemen, if I leave a letter in the first slot, notice that letter could repeat. So there's 5 ways of populating the second slot of this ID card. Times there's 5 ways to populate the third slot. Times there's 5 ways to populate the fourth slot. So there's going to be 5 times 5 times 5 times 5 number of different 4-letter ID cards if repeats are allowed, or that's 5 to the 4th power. Or that's going to be 625 different ID cards. That are possible. There's 625 different ID cards that are possible there. Everybody see that there? Now, to enumerate all 625 would not only take an exuberant amount of time, the chance of getting them correctly enumerated would be virtually almost non-existent. A human would have a very difficult time enumerating all 625 different ID cards that can be formed from these 5 different letters, assuming that we can have repeats. So I'm not going to enumerate all of them. One ID card, I'll maybe enumerate a couple of them. One ID card could be A, B, C, D. Another one could be D, A, B, C. Another one could be C, D, A, B. Okay, just to name 3 of them. But there's 622 more of these. Okay, so that would take a while to try to enumerate all the possibilities. All righty. Is this making sense so far? The fundamental principle of counting. if the first thing can occur 5 ways, second thing can occur 5 ways, third thing can occur 5 ways, and the fourth thing can occur 5 ways, then the total number of different sequence that can be arranged here would be 5 times 5 times 5 times 5, or 625 different arrangements of the sequences of these letters to form 4 letter IDs. Right? Fundamental principle of counting here. Now, B, how many cards are possible if each letter can only be used once? You think there's going to be more possible ways or less possible ways if each letter can be only used once? What do you think? More or less than 625 different ways? Assuming we cannot use any letter more than once.
Less.
Less, you are correct. There will be quite a few less. In other words, how many different ways can I occupy the first slot of my 4-letter ID card? There's 5 ways, correct? Times, but ladies and gentlemen, if I leave one of the 5 letters in slot 1, then I only have 4 letters left to occupy the second slot. But now I've left 2 letters out of the batch of 5, and therefore it leaves me with only 3 letters left to occupy the third slot. But now I've left 3 letters of the 5 out, and I only have, 2 left to occupy the last slot. So there will be 5 times 4, which is 20, times 3 is 60, times 2 is 120 different ID cards that can be constructed if letters cannot be repeated. Only 120 compared to 625. And again, trying to enumerate even 120 would be very, very difficult and time consuming. All right, is this making sense so far? The fundamental principle of counting. All right, now, ladies and gentlemen, in order for us to enumerate things a little bit more conveniently, we oftentimes use a fabulous function for mathematics called the factorial function. Okay, and this is the factorial function here. We read this notation in mathematics as n factorial. N factorial by definition is equal to n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times ... times 2 times 1. That's the definition of n factorial. Where n, for our cases, is going to be some sort of an integer, okay? All right, so let's go look at some examples of how this factorial plays out here. So what would 1 factorial be? 1 factorial is going to be 1. 2 factorial is 2 times 2 minus 1, or 2 times 1, or 2. 3 factorial is 3 times 3 minus 1, which is 2, times 3 minus 2, which is 1. 3 times 2 times 1 is 6. 4 factorial is 4 times 4 minus 1, which is 3, times 4 minus 2, which is 2, times 4 minus 3, which is 1. 4 times 3 is 12, times 2 is 24, times 1 is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. You can see that factorials grow very, very quickly, okay? Any questions about the factorial function so far here?
Can you go back over that, please?
All right, well, by definition, what is n factorial? N factorial is always equal to n times n decreased by 1 times n decreased by 2 times n decreased by 3 times n decreased by 4 times ... all the way to get down to times 2 times 1. Okay, so what's 7 factorial going to be? It's going to be 7 times 7 minus 1 times 7 minus 2 times 7 minus 3 times 7 minus 4 times 7 minus 5 times 7 minus 6, which is to say 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what 7 factorial will be. And that's gonna be a big number. What is 7 times 6 times 5 times 4 times 3 times 2 times 1? That's 5,040. So that is the factorial function, ladies and gentlemen. You can see that factorials grow very quickly, a lot quicker than a linear rate. They even grow quicker than an exponential rate. Okay, they grow very, very quickly. Could you imagine trying 100 factorial? No, 100 factorial would be 100 times 99 times 98 times 97 times 96 times 95 times 94 times 93 times 92 times 91 times 90 times 89 times 88 times 87 times ... all the way to get down to 2 times 1. That is going to be a humongous number. Okay. In fact, most calculators cannot handle a number this large. You would get an overflow error in your calculator because the registers are only so large to accommodate numbers of a certain size. That'd be an overflow with most calculators. There are some scientific calculators out there that can handle a number this large, but most of them cannot. All right, is this factorial function making any more sense here? A factorial is just a number, right? There's the definition. Now, as odd as it may seem, ladies and gentlemen, 0 factorial is not equal to 0. It's not. Common mistake or pitfalls to think that 0 factorial is equal to 0. It's equal to 1 by definition. Don't forget that. 0 factorial is equal to 1. All right. Some of the formulas we'll be working with require division of factorials. This will be simpler or more simply done if we basically can think of the factorial more robustly. For instance, if I have like 5 factorial divided by 4 factorial, what would this simplify to? Well, do you agree that 5 factorial is 5 times 4 times 3 times 2 times 1? 4 factorial is 4 times 3 times 2 times 1. Do you agree the 1's reduced, the 2's reduced, the 3's reduced, the 4's reduced? And we're left with 1 down here in the denominator. So we're left with 5 over 1, which is 5. Everybody see that there?
Yeah.
There's a simpler way of having simplified this. Let me show it to you. Simpler way would be going like this. Ladies and gentlemen, in doing this a more efficient way, I could have thought as 5 factorial as being 5 times what? What's another name for 4 times 3 times 2 times 1? Anybody? What's another name for 4 times 3 times 2 times 1? What's another name for this? What factorial is this? What factorial is 4 times 3 times 2 times 1?
Factorial 4.
4 factorial. Do you agree? So I could have rewritten 5 factorial as 5 times what? 4 factorial. 4 factorial being all this. And this is divided by 4 factorial. Now what happens to the 4 factorials? What happens to these?
They cancel out.
You reduce the 1's. Yeah, and you're left with 5. See how more efficient that was than doing it this way? See? Let's try another one. Suppose I had 100 factorial and I wanted to divide that by, let's say by 95 factorial. Well, do you agree 100 factorial is 100 times 99 times 98 times 97 times 96 times 95 times 94 times 93 times 92 times 91 times 90 times 89 times 88. In other words, it's 100 times 99 times 98 times 97 times 96 times 95 what? Factorial over 95 factorial. What happens to the 95 factorials?
Cancel out.
You reduce. And so therefore 100 factorial divided by 95 factorial is going to be just 100 times 99 times 98 times 97 times 96 I'm gonna try that on my basic scientific calculator and see if my machine can handle that size number. 100 times 99 times 98 times 97 times 96. Yeah, it can. It's a big number though. Anybody want to read that number? What 100 factorial divided by 95 factorial gives us? How do we read that number? Anybody? Anybody want to read that number for us? I put the commas in for readability purposes. Ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. What place is this?
Billions.
Billions. 9 billion, 34 million, 502,400. Okay, that would be equivalent to 100 factorial divided by 95 factorial. All right, is this making any sense here, Liz, on how I'm simplifying quotients of factorials by rewriting the factorials in a more convenient, compact way, and then being able to reduce a little more efficiently?
Yes.
All right, I just want to show you that now. Now, hey, if you don't like doing things the long way here, to the rescue is, well, wait a minute, this is Math 115. Okay, well, I'll tell you what, we still have access to the TI, what, 30 or 34, don't we? I think we got factorials on our calculator, ladies, on our basic scientific calculator. Let me show you, this is the TI 34 here, okay? Now, it's similar to the TI 30. And look, well, let me see here. Like I said, I don't have any batteries in this TI 30 here. But where does the factorial hang out in the TI 30? I'll tell you what, I'll bet dollars to donuts, because look at my TI 34. My TI 34 has a probability button on it. You see that button, PRB? That's short for probability. And this is on the TI 34. When I hit that button, notice my third function down is my factorial function. Everybody see that there? Probability, third function down is the factorial function. Well, guess what? Your TI 30 XS also has a what button on it? Probability button. Now, I don't have any batteries in this thing, but I bet if you push that probability button, you would see the factorial function. Does anybody in this class have a TI 30 XS?
I do.
If you hit the probability button, do you see that factorial function?
Yeah. I do.
You see that? Good. Well, that's going to help our cause. So let's do this problem on our calculator, ladies. How could we have used our machine to help us out here? Well, here's how. Here's how I would do it on my TI 34. It's done probably the same way on the TI 30. You hit your probability button first. Oh, wait a minute. No, not first. Clear your screen. We have to type in 100. I'll tell you what, I'm going to enclose this inside parentheses for safety. 100. Now we got to go get the factorial function. So I hit my probability button. And I got to go down, scroll down to get the factorial function. Enter. 100 factorial, closed parenthesis. Whoops. Closed parenthesis. Divided by 95 factorial. Open parenthesis. Oops, hold on. Open parenthesis, 95, got to go get the factorial function, probability, factorial, closed parenthesis, enter, and here we go. Boom. What? That's overflow? All right. Here's why it's overflow, ladies and gentlemen. Because remember, I told my calculator to do 100 factorial. Let me ask you this. Is 100 factorial a big or small number? 100 times 99 times 98 times 97 times 96 times 95 times 94 times 93 times 92 times 91 times 90 times 89 times 88 times 87 times 86 times 85 times 84 times all the way down to 2 times 1. Is that a big or small number?
Big.
This is colossal in size. In fact, it's so big that my TI-34 multi-view basically crashed. You everybody see that there? Overflow error. Can't handle it. Then how did I get this number? Oh, because I just told my TI-34 to just do 100 times 99 times 98 times 97 times 96. My machine can handle that. So I sit corrected. On some of your scientific calculators out there, to negotiate a problem like this, you may have to write it like this and cancel out the 95 factorials and then just do the 100 times 99 times 98 times 97 times 96. Does that make sense to give you this? You may have to do this. You may not have a choice because your calculator cannot handle 100 factorial. It's too big, right? Too big of a number. I wonder if the TI-84, which is a little bit more advanced of a scientific calculator, can handle a number that big. I'm going to try it on the TI-84 just for the heck of it, see what happens. This is a TI-84 graphing calculator. If you get into college algebra and beyond at Mott, you'll get to use this. So I'm going to try it out. 100 factorial. I hit my stat button. Wrong. Try that again. 100 factorial. I have to hit my math button. Then go over to my probability menu, PROB, and there's the factorial waiting for me down there. 100 factorial divided by 95 factorial. So math, probability menu, go down and grab the factorial function. Enter. Even on the TI-84 plus C Silver Edition, ladies and gentlemen, there's an overflow error. The calculator cannot handle 100 factorial. It's just too big of a number. Let me just try that one more time. 100 factorial. Let's see if my calculator can just handle that. Nope, overflow error. Can't handle it. Now, there is a TI-85 calculator out there, or TI-86 or TI-89, which I think can handle that, but it's going to report it in scientific notation form as a very, very big number. All right. So the moral of the story is this. If you're given a problem like this, ladies and gentlemen, in this class, maybe on Alex, where they want you to evaluate this 100 factorial divided by 95 factorial, you're going to have to write it like this. You're going to have to do what I did here to get rid of the 95 factorial so that it's manageable on your calculator then. Okay? Everybody see that there? You may have to do this. We might not have any choice. All right, so this is a good thing that I'm showing you this, how to negotiate something like this by rewriting your factorial there. All right. So for classwork number 1, let's see if you can do this problem here. We'll call this classwork number 1. I want you to evaluate this. All right, how about, how about 95 factorial divided by 90 factorial? All right, ladies and gentlemen, go ahead and try that on your calculator or whatever. Before you try it on your calculator, you may have to rewrite this. Go ahead. We'll call that classwork 1. See if you can negotiate that and evaluate that, what that's equal to. All right, so the only way to negotiate this one on your calculator is to probably write the numerator as 95 times 94 times 93 times 92 times 91 times 90 factorial. And then divide this by 90 factorial, and the 90 factorials then drop out to 1, reduce out. And now you can do this on your calculator, okay? Your calculator will handle this, I think. So what is 95 times 94 times 93 times 92 times 91 times, well, what do we get? Big number? Are we all getting this here? What is that? 6,952,862,280. Did we all get that? Is it making any sense?
I did.
Okay, good. All right, I just want to show you how to handle something like this. All right, you're going to have to do this because your calculator cannot handle a number of the size of 95 factorial or even 90 factorial for that matter. So you got to do this. All right. All right, let's move on now. All right, this is just more practice here on the PowerPoint. If you want to, take the time to look at that, there's a little bit more practice there, Liz, on with the factorial. All right, now we're going to define for ourselves what a permutation is. Okay, and a permutation is an arrangement of n distinct objects. What does it mean to say distinct? That the objects are distinct. What does that mean? N distinct objects. Distinct means what? Well, let me give you a hint. You are distinct from me, and I am distinct from you. What does that mean?
Distance.
We're not the same. Do you agree? Distinct objects means they're all unique objects. They're not the same objects, okay? They're all different. So a permutation is an arrangement of n distinct objects in a specific, here's the key, in a specific order, where order matters. This is called a permutation. Here's an example. Suppose that a photographer wants to arrange 3 people, Carmen, Juan, and Christina, in a specific order for a portrait. How many different ways, ladies and gentlemen, could we arrange these 3 people for a portrait? Well, you could envision this as having 3 chairs. Chair number 1, chair number 2, and chair number 3. We have 3 people to choose from. We have Carmen, Juan, and Christina. Okay. One arrangement would be what? We could have, what were their names again? What was the first name again? It was Carmen. We could have Carmen in chair 1, Juan in chair 2, and Christina in chair 3. What's another possibility here? I could have Christina in chair 1, Carmen in chair 2, and Juan in chair what? 3. Or I could have what? Juan in chair 1, Christina in chair 2, Carmen in chair 3. Any other arrangements? Well, I could have Juan in chair 1, Carmen in chair 2, and Christina in what? Chair 3. Do you agree? Or, ladies and gentlemen, I could have what? Christina in chair 1, Juan in chair 2, and Carmen in chair 3. Do you agree? And there's one other arrangement. Anybody know what the last arrangement would be? I've enumerated 5. I gave you a hint. There's one more. Well, I could have Carmen in chair 1, Christina in chair 2, and Juan in what? Chair 3. Do you agree? There's 6 different ways, ladies and gentlemen, of arranging these 3 people into a different portrait. 6 different ways. Let me see that there. Now, here's a way of representing the number of ways in which we could arrange 3 people in a specific order for a portrait. Think of us as having 3 slots. Chair number 1, 2, and 3. How many ways can I occupy chair number 1 with 3 people? How many ways can I seat 3 people in chair number 1? 3 ways. 3 ways. Do you agree? I got 3 people to choose from. Times, but I leave this person out. I leave one of my persons out in chair 1, and I only have 2 more people to what? To populate chair 2. But now I left 2 people out. Times, so that leaves only 1 person left to occupy the 3rd chair. So, ladies and gentlemen, according to the fundamental principle of counting, there's 3 times 2 times 1, or there's 6 different ways of arranging 3 people in a specific order. 6 different ways. That's called a permutation. Okay. Any questions with the number of different ways and the different enumerations of arranging 3 people in a specific order for a portrait, if the chairs were labeled and they had a different significance? Okay. So order matters there. And here are all the possibilities. There are 6 possible abilities. They've enumerated all of them. And so there's 3 times 2 times 1, or we know that better as 3 factorial ways, ladies and gentlemen, of arranging 3 people in a specific order for a portrait. Here's the question now. Based on what you just seen there, how many orders do you think there would be for 8 people? In other words, how many different ways can I arrange 8 people for a portrait? You've seen how this one was done with 3 people, right? So how many different ways would there be to arrange 8 people in a specific order? You would say not 3 factorial, but 8 factorial ways, 40,320 different ways of arranging 8 people in a specific order. Because again, think of it as being like 8 chairs, 2, 3, 4, 5, 6, 7, 8. How many different ways can I seat these 8 people in these 8 chairs if these chairs have a distinction between each other? They're not the same arrangement. Well, how many ways can I populate with 8 people the first chair? There's 8 ways because there's 8 people to choose from. But I leave one of the persons out, so I only have 7 people left to choose to populate the second chair. But now I left 2 people out, which means there's only 6 ways to populate the 3rd chair, 5 ways to populate the 4th chair, 4 ways to populate the 5th chair, 3 ways to populate the 6th chair, 2 ways to populate the 7th chair, and 1 way to populate the 8th chair. Ladies and gentlemen, this is better known as what factorial? Do you recognize it? Isn't that 8 factorial? And if you work 8 factorial out on your calculator, you'll discover that there's 40,320 different ways of arranging these 8 people in a specific order for a photograph. Could you imagine trying to enumerate all 40,320 different ways? You ever see that Snickers commercial they used to have on in the past? Gonna be a while. Okay, that'd take a tremendous amount of time. And your chance of getting all the enumerations correct would be virtually impossible because you couldn't even remember what was the 320th arrangement or the 319th arrangement. You'd lose track of what's what. This would be an impossible problem for a human to do. Unless you got a computer brain, literally. There's not too many floating around like that. All right, the number of permutations of n distinct objects using all of the objects is nothing more than n factorial. This is a general rule. So if I had 100 people and I wanted to determine how many different ways I could arrange these 100 people in line, in a specific order, in some sort of a line, there would be 100 factorial different ways of arranging 100 people in a specific order in a line or a queue, okay? That'd be a lot of arrangements, a lot of possibilities. There'd be no way you could arrange all these different possible arrangements as a human. Computers can deal with this, but humans cannot deal with something like this. All right, here's another beauty. There are 7 horses in a race and a large jackpot for anyone who can pick the finishing order of all 7 exactly right. Is this a difficult problem, ladies and gentlemen? Find the number of possible orders that they can finish. In other words, one horse is going to finish in first place, the other in second place, another in third place, one in fourth place, one in fifth place, one in sixth place, and one in seventh place. How many different orders can these 7 horses finish? How many different specific orders can you arrange these 7 horses from first place to 7th place? You would say what factorial? Anybody? What would we say? What factorial?
7 factorial.
7 factorial. All right, get on your calculator, ladies and gentlemen, and I want you to dial up 7 factorial for me right now. Go ahead. What is 7 factorial? Just use your factorial function. It'll speed things up here.
I got 540. I think I do.
All right. You got 5,040? Yeah.
Yes.
There's 5,040 different ways, ladies and gentlemen, of having these 7 horses finish in a specific order from first place to 7th place. So look at, if you bought one ticket that had these 7 horses finishing in one specific order from first to 7th place, your chance of winning the jackpot, ladies and gentlemen, would be 1 over 5,040. That's the probability of you having the winning ticket, because there's only one order that will win the jackpot, one specific order. There's 5,040 different possibilities. You choose only one ticket with one order, your chance of winning is this. And if you were to turn that into a percent, your chance of winning would be 0.02% chance of winning. That's 0.02 of 1% chance of winning. That's not even close to being a 1% chance of winning. That's only 0.02 of 1% chance of winning. So you can see that gambling is obviously, it's a gamble to say the least, okay? Your chances or odds of winning this jackpot would be very slim. Even if you bought, let's say, 100 tickets, 100 different arrangements in which these horses could finish from first to 7th place, your chance would be 100 over 5,040. Does that improve your odds? Yes, it does. Does it improve your odds markedly? Well, you would only have a 1.9% chance now of winning if you bought 100 tickets with 100 different arrangements in which these horses could finish from first to 7th place. Even with 100 tickets, could you imagine if these tickets cost $10, ladies and gentlemen? That'd be $1,000 you lay out, and you only have a 1.9% chance of winning a jackpot. Still, your odds are slim to none. Do you agree? That's when you lay out $1,000 just to buy the tickets. There's 100 different arrangements. So yeah, you might want to do your homework first before you gamble, unless you have money to burn. Then that's a different ballgame. Okay. 5,040 different possible finishing orders for these 7 horses. Here's another one here. And ladies and gentlemen, I want you to do this problem. This will be classwork number 2. How many different ways can a pledge class with 20 members choose a president, a vice president, and a Greek council representative? No pledge can hold 2 offices. So look at, there's 3 offices to fill. You got president, you got vice president, and you have the office of a Greek council. You have how many people to choose from? 20. All right, you go ahead. This will be classwork number, what is it, 2, I think. How many different ways, ladies and gentlemen, can I arrange 20 people in a specific order? One to be president, one to be vice president, and one to be a Greek council representative. Go ahead. Classwork number 2. Well, let's see. How many different ways can I seat a president from 20 members? There's 20 different ways. But if I leave one of these people out as president, I only have 19 left to seat as vice president. But now I've already filled the office of president and vice president. That leaves me 18 people left to fill the office of the Greek council representative. Here's the number of ways, ladies and gentlemen, that you can fill these 3 offices with 20 people. And what is 20 times 19 times 18? Gives you 6,840 different ways to seat 20 people. One as president, one as vice president, one as Greek council. Is this making any sense here, what we're doing? Fundamental principle of counting so far, and the permutation rule here. Did anybody get this? Curious.
Yes.
All right. Great. Okay. All right. Well, ladies and gentlemen, we have a specific formula that can compute a permutation to compute the arrangement of n distinct objects in a specific order using r of those objects without replacement is called a permutation of n objects taken r at a time. It is written symbolically as NPR. Okay, so how do we read this notation here? This is read as n permuted r ways. N permuted r ways. And it is calculated using this formula here. N permuted r ways is equal to the ratio of n factorial divided by n minus r factorial. All right. Now, let's see if we can do the last problem over again. There were 20 members to choose from, and we have to seat one as a president, one as a vice president, one as a Greek council representative. So we have 20 people to choose from, and we got to choose 3 of the 20. So how many different permutations, ladies and gentlemen, are possible from 20 people if you choose 3 at a time? Well, that's called 20 permuted 3 ways. Notice the notation here, 20 permuted 3 ways. And by our formula, it's going to be 20 factorial here divided by 20 minus 3 factorial. So that's going to be 20. Do you agree? 20 factorial divided by what? 17 factorial. Now, what's the easy way to negotiate this? You remember the little trick I showed you? I would write this as 20 times 19 times 18 times what? 17,
17.
yep, 17 factorial. Do you agree? And it's
Yeah.
divided by 17 factorial. So what happens to the 17 factorial here?
They cancel out.
Drop out. Get on your calculator now and dial this up. What's 20 times 19 times 18? You got your answer. 20 times 19 times 18. That gives you 6,840 different ways to seat 20 members. One is president, one is vice president, one is Greek council representative. Isn't that the same answer we got on the previous slide?
Yes.
Look what's happening here. All right. Hey, ladies and gentlemen, we don't even have to do this business. Because on our calculator, we have a wonderful function built in called the permutation function. It can take care of all this in one swoop. And let me show you how to do this on the TI-34, which is done probably the same way on the TI-30, no difference. All right, first of all, what I'm going to do is I'm going to basically type in 20. I'm going to hit my probability button, PRB. And then I got to go get my NPR function. That's your permutation function. And then I got to type in what R is. R is 3. And then hit enter, ladies and gentlemen, and boom, you will get this. Okay, so let's try this out on our calculator here. 20, probability button, NPR function, 3. All right, here we go. 20, probability button, NPR function, that's your permutation function, 3. The 20 takes the place of the N, the 3 takes the place of the R. Hit enter, boom, you got your answer, 6,840. See how much quicker that is than using all that factorial business? Look at that wonderful function. Isn't that amazing? Does it work the same way on the TI-30?
Yes.
All right, good. Well, that's good to know. It works the same way. All right, that's called your permutation function. All right, here's an example. In a lottery game, 40 numbered ping pong balls are put in a bin. They're all mixed up and they bounce around in a haphazard, random fashion. Does anybody out there play bingo? You must be like me then. You're right, ladies. I used to play bingo, but I no longer play bingo because I am convinced that if I was the last person on planet Earth playing the bingo game, I still could not win. Still couldn't win. Okay. Really? Seriously? There's nobody out there that plays bingo? Because I know a lot of people that do. All right. Anyways, in a lottery game, 40 numbered ping pong balls are put in a bin. Each of these ping pong balls have a number on it, 1 to 40. Okay. 4 are randomly chosen, 1 at a time. To win the game, players need to match all 4 numbers in order. That's the key, in a specific order in which they are drawn. How many different winning orders are possible here? So in other words, ladies, one possible order could be, you could have maybe chosen a ticket that has 10, 20, maybe 27, and maybe 40 in this specific order. If that's the winning ticket, and if you had that specific order, you win the jackpot, okay? If you chose a ticket that is 10, 27, 20, and 40, guess what? You don't win the jackpot because your numbers are not in the required order. Order matters here. You see that? Stop and think, ladies and gentlemen. With 40 different numbers, how many different ways are there to arrange 40 different numbers 4 at a time in a specific order? Would you think that number is going to be big or small? You think there's a lot of arrangements here or not many?
Big?
There's a large number of possibilities. Do you agree? To arrange
Yeah.
40 numbers in a specific order 4 at a time. Let's find out exactly how many. It's easy to do that. We use our permutation function. So we type in 40, permuted 4 at a time. Use your calculator, ladies and gentlemen. 40 permuted 4 ways. You tell me how many different ways are possible to arrange 40 numbers in a specific order of 4 at a time. It's a big number.
Thanks for cleaning the kitchen.
All right, so did we get this number?
Yes.
2,193,360 different ways of arranging 40 numbers in a specific order, 4 at a time. Do you agree? If you buy 1 ticket to play this lotto, ladies, your chance of winning the jackpot is 1 divided by that number of possibilities. That's with 1 ticket. You know what? Even if you buy, like, let's say 5,000 tickets, which is going to cost a lot of money, your chances are still almost non-existent. Isn't that unbelievable? There you go. All right, there's a lot of different ways, ladies and gentlemen, of arranging 40 numbers in a specific order, 4 at a time. So if nothing else, we're seeing that how difficult it is to win some of these lottery games here, ladies and gentlemen. It's almost like if you win, well, you were pretty much meant to win, simply put. You have a better chance of getting struck by a lightning bolt walking to your car than winning the lotto, in all honesty, or having an F5 tornado come right through your living room. Oh, there are no F5s, by the way, but you still have a better chance. All right, any questions about that? All right, let's move on. Okay, now I want to show you something else here. Suppose I have a 3-letter word. ABBA. A-B-A. All right, ladies and gentlemen, I got a question for you here. Okay, the question is, how many different ways can I arrange the word ABBA, these letters in the word ABBA, so that I have a unique arrangement? Well, check this out. If I actually called this A my number 1A and this A my number 2A, if I rearrange the number 1 and 2 A's, will I have a unique word? Does this word look any different than this word here?
No.
They're the same, aren't they?
Yeah.
You see, the problem is we have repeated letters here. So if you call this arrangement different than this one, you'll be double counting this arrangement, which really is one and the same. Okay, they're the same arrangement. They're not unique. Okay, to have unique arrangements here, how many possibilities are there? Well, I could have ABA. I could have AAB. I could have BAA. Do you agree these are 3 unique arrangements of these 3 letters in this word?
Yes.
Now, again, if this is the number 1A and the number 2A is here, this arrangement would not be unique. To say I move the number 2A here and the number 1A here. This is the same as this arrangement, so we don't count this guy. Likewise, if this is the number 1A and the number 2A, if I had the number 2A first and then the number 1A second and then B, guess what? This word looks identical to this word. This is not unique from this. Likewise, if this was the number 1A and the number 2A, if I add B and the number 2A and then the number 1A, guess what? This word is identical to this. It's redundant. So you don't count these. These are repeats. Do you agree? Repeats. All right, so ladies and gentlemen, we got to be careful when we are trying to enumerate a permutation where we have repeated letters or characters. Okay, in that case, we have to use this rule here. N factorial divided by R1 factorial, R2 factorial, R3 factorial, times RK factorial. In other words, we have to divide out the repeats, okay, or cancel out the repeats here. Because we don't want to double count these words are the same word. Likewise, likewise. All right. So how many letters do I have here? I have what? 3 letters, correct? I have 3 letters. Now, the letter A repeats how many times? The letter A repeats what? 2 times. So this is going to be divided by 2 factorial. Times, technically, the letter B repeats 1 time. Technically, times 1 factorial. This is going to be the number of ways of arranging these 3 letters, okay, in a unique fashion. And it should be 3 different ways. That's it. Let's see if this comes out to be 3. 3 factorial is 3 times 2 factorial, is it not? That's divided by 2 factorial. 1 factorial is just 1. What happens in 2 factorials? They cancel. We're left with 3. And there you go. Sure enough, ladies and gentlemen, there's only 3 different arrangements of these 3 letters that will form a unique word. A unique word. Unique. These are not unique. These are not unique. These are not unique. That's why we're going to divide by 2 factorial times 1 factorial to reduce the possibility of double counting non-unique arrangements. Everybody see that there? So we got to be careful when we have repeat characters or letters. And so on the PowerPoint presentation, we run into this rule in general here. They're using K sub 1, K sub 2. I used R sub 1, R sub 2. Same thing. The number of permutations of n objects in which K1 objects are alike, K2 objects are alike, etc., is found by using this rule here. Okay. All right, here's a beauty. Classic example. How many different passwords can be made using all of the letters in the word Mississippi? Wait a minute here. We have a lot of repeated letters, don't we? S repeats how many times? How many times does S repeat? 4 times, doesn't it?
Yes.
I repeats what? 1, 2, 3, 4. I repeats 4 times also. And P repeats twice. So, ladies and gentlemen, I got a question. If I just rearrange these 2 S's here, just flip these 2 S's here, just these 2 S's, do I have a unique word, or is it still the same as the original word?
Still the same.
Still the same. So that's not a unique arrangement. It's not a unique word just by flipping these 2 S's. Likewise, if you just flip these 2 P's around, you still got the same word because you got repeated letters here. So how many different words can we form from the word Mississippi? How many different unique words or passwords can we form from the word Mississippi? Well, let me ask you this. We're going to have to use our rule that we established above there. How many letters are in the word Mississippi total? The total number of letters. There is what, 11 letters? So 11 factorial divided by, how many times does M repeat?
1 time.
1 time. So this is divided by 1 factorial. Times, how many times does I repeat?
4.
4 times. So times 4 factorial. Times, how many times does S repeat?
4.
Times 4 factorial. And did I get P? No, I didn't get P. P repeats what? Twice, doesn't it? So that'd be times what? 2 factorial. This is the number of ways of forming unique words from all the letters in the word Mississippi. Okay. So how would we negotiate all this on our calculator here? Because it looks like a lot of madness, to say the least here. How would you, dial this up on your machine here? Well, you could maybe help yourself a little bit if you rewrite 11 factorial maybe as 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. Do you agree? And this sits over what? Forget the 1 factorial. 1 factorial is just the 1. This sits over 4 factorial times 4 factorial times what? 2 factorial, correct? What happens at least with the 4 factorials? We can get rid of them, can't we? Those are gone. And then we're gonna have 11 times 10 times 8 times 9, excuse me, times 8 times 7 times 6 times 5. And this is gonna sit over, we still got a 4 factorial here, don't we? Don't have any choice, but that's still gonna be, that's gonna be 4 times 3 times 2 times 1. 2 factorial is 2 times 1, so we got another times 2 times 1. Yeah, ladies and gentlemen, you gotta get on your calculator and dial this up now. Make sure you enclose your numerator inside parentheses and your denominator. Go ahead and dial it up and make sure that you can compute the number of unique different passwords that can be formed from the word Mississippi. That's going to give you your answer when you bring this up on your calculator. So we got to dial this up here. So it's going to be 11. Or you know what? Even an easier way, because by rewriting 11 factorial is 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial. This is still a lot of work to have to do 11 times 10 times 9 times 8 times 7 times 6 times 5. You know what? You could just do this on your calculator, ladies and gentlemen, but I strongly recommend you enclose this inside parentheses. Very important to put your numerator and denominator inside parentheses. So just do it this way here. 11 factorial divided by in parentheses 1 factorial times 4 factorial times 4 factorial times 2 factorial. You'll have your answer. Let's see if we can do that on our machine. All right, when I work it out on my calculator here, I'm getting 34,650 unique words that we can form from the word Mississippi. They're unique words. They're all different. They're not the same. No repeats, no redundancy. Did anybody compute that by chance? When you dial this up here?
Yes.
That's a lot of different possible passwords, isn't it? Even for the word Mississippi, even regardless of the repeats we got going on in here, a lot of repeated letters. There's still a lot of possible different passwords. All right. So hopefully you can do this on your calculator, negotiate it, get that 34,650 one way or another. And if you think I'm going to sit here and enumerate all 34,650, think again. After all, it is Halloween. Okay. There's a lot of different ways, ladies and gentlemen, of rearranging those letters in the word Mississippi. But notice all the repeats we got in the letters here. So you got to erase all those and make sure you account for the redundancy of the repeats. Don't count them. All right. Well, let's see if we can go have some fun to wrap up the remainder of this session here. We will go to our textbook here. See if we can do a couple of problems out of our textbook. This is section 10.2 entitled The Fundamental Counting Principle and Permutations. Okay. Here we go. We'll go down and do a couple problems. As always, take the time to look over some of these wonderful examples. Notice the trees that they're building are actually top-down trees. Mine were sideways trees. Okay, but trees are a nice way of enumerating different arrangements of things. Okay, and there's your factorial, of course. We looked at that, all right? And they work out some examples here. There we go, different arrangements of people to take a photograph. We've already looked at that example. Permutations, in fact, there's the permutation function, all right? So it was all on the PowerPoint. Let's try to do a couple problems down here in the exercises. All right, I want you to do problem number 34. This is classwork. I don't care what classwork you call it. Just make sure you hand it in. This will be one of your classworks here, Liz Owen. So number 34. Everybody do this. Out of a group of 8 students serving on a student government association, how many different ways can a president, a vice president, and a treasurer be selected? Go ahead and figure out the number of ways. That'll be a classwork problem, number 34. Well, you have 8 people to choose from, and you need to fill the office of president, vice president, and treasurer. You have 8 ways to fill the office of president. You leave one person in the presidency slot. You have 7 different ways remaining to fill the vice presidency slot. You left 2 out now. You only have 6 different ways remaining to fill the treasurer spot. There's 336 using the fundamental principle of counting. Or, ladies and gentlemen, it would be 8 permuted 3 ways, which is 336. Anybody get that there? 336 different cabinets are possible to form here from 8 people.
Yes.
Okay. So hopefully this is making some sense here with these permutations or the fundamental principle of counting.
Good.
All right. That was 34. Throw number 40 into the mix here. Go ahead and do that one. We'll just put it, throw it into the rest of our classworks there. Go ahead and figure out that one. All right, so you got 7 different lab experiments to assign to 5 different people in a specific order. There's 7 ways to assign lab number, 7 ways of assigning a lab to like person 1, 6 ways to assign a lab to person 2, 5 remaining labs ways of assigning to person 3. 4 different labs can be assigned to person 4, and 3 different labs can be assigned to person 5. For possible number of arrangements in a specific order of 2,520, or this would be 7 permuted 5 ways, which would also give you 2,520. So there's 2,520 different ways of basically allocating these 7 labs to 5 people in a specific order. Anybody come up with that? One such order could be like, maybe this person gets lab 5, and maybe this person gets lab 6, maybe this person gets lab 7. Maybe this person is assigned to do lab 3, and maybe this person's assigned to do lab 2. That's just one among 2,520 different ways of assigning these labs to 5 different people in a specific order, okay? All right. All right, that's one like number 40. Number 41, you can roll that in your classwork. A radio DJ has a choice of 7 songs in a queue. A queue, ladies and gentlemen, is a waiting line. That's another name for a waiting line, is a queue. A specific ordered arrangement is called a queue. He has to pick 3 different songs to play in a certain order after the commercial break. How many ways can he select the 3 different songs? Number 41, throw that in your classwork. Well, there's 7 songs to choose from, and you want to play them in a specific order, 3 at a time. Okay, and so there would be 7 times 6 times 5, or 210 different ways of playing 7 songs in a specific order where you play 3 at a time. That's also can be found by either using the fundamental principle of counting, or you could use the permutation rule, 7 permuted 3 ways, 210. Okay. All right. That's another classwork. Okay, let's turn the page. All right, number 43, try this problem. A nursing student can be assigned to one of 6 different floors each day, depending on staffing needs. How many different ways can a student be assigned during a 5-day work week? Try number 43. That'll be another classwork. Okay, so for this problem here, it comes down to how many different ways can you assign 6 floors to the 5 different days of the work week? Okay, so like on Monday, there's 6 ways to assign a floor. On Tuesday, having assigned one on Monday, there's only 5 floors left to assign on a Tuesday, but now you've assigned 2 floors. There's only 4 floors left to assign on the third day, Wednesday. But now you've assigned 3 floors, so you only got 3 floors left to assign for Thursday and 2 floors left to assign for Friday. So 6 times 5 times 4 times 3 times 2, 720 different ways of assigning 6 floors over a 5-day work week. And that could also be found or computed by using the permutation function. 6 permuted 5 ways is equal to 720. Okay. Anybody get that? Anybody get 720?
Yes.
Good. 47, here's an interesting question. How many different code words can be made from the symbols? We have 3 asterisks, 2 ampersands, $1 and 2 pounds, 3 pound symbols, 4 pound symbols, excuse me. If each word has 10 symbols in it, ladies and gentlemen. Now they have to be different. They have to be unique. Okay. They cannot be repeated codes. So here's a hint. You can't just switch any 2 of these pound symbols and call it a unique password or a unique code. That would be redundant. That would be a repeat. Okay. They have to be unique codes. So I want you to try to figure out, okay, how many unique codes we can form of size 10 from all of these symbols that we have at our disposal. All right, go ahead and work that problem out. This will be a classwork problem, number 47 here. Well, let's take a look here. We have 10 total symbols here at our disposal, and our code word has to have 10 characters in it. 10 of these symbols in it. But the thing is we have a lot of repeats here. So like we have the asterisk that repeats 3 times. The ampersand repeats 2 times. The dollar symbol repeats 1 time, and the pound symbol repeats 4 times. So the number of unique or different codes that can be formed, okay, from these 10 symbols would be 10 factorial divided by 3 factorial times 2 factorial times 1 factorial times 4 factorial, which would give you 12,600 different or unique codes of size 10 that could be formed from these 10 characters. Okay, did anybody get 12,600? Anybody crank that out? Well, if you didn't, hopefully you can see that now. All right, so when you have redundancy, you have to divide by the redundancies, okay? All right, that one's done. Number 48. Let me erase all this here, get this out of your way. All right, I would like you to do number 48, throw that into the classwork. How many different passwords can be made from the letters in the word Alabama? Question, is uppercase A distinguishable from the lowercase a's? Yes or no? What do you think?
Yes.
Yes. Key observation. So ladies and gentlemen, that uppercase A is different than the lowercase a's. All right, you go ahead, figure out how many different passwords can be made from all the letters in the word Alabama. Okay? They have to be different or unique passwords. No repeats, no redundancy. All right, go ahead and figure out how many you can arrange. Okay, so we have 7 letters to choose from in the word Alabama. Okay, notice uppercase A repeats once, Lowercase a repeats 3 times. Lowercase b, L, and M all repeat 1 time. So the total number of different passwords that you can form from the word Alabama, or unique passwords, would be 7 factorial divided by 1 factorial times 3 factorial times 1 factorial times 1 factorial times 1 factorial. Now, the 1 factorials are all nothing but factors of 1. So technically, you can just compute this as 7 factorial divided by 3 factorial. And what's 7 factorial over 3 factorial? Well, that's going to give you 840. So there's 840 unique passwords you can form from the word Alabama. Okay, anybody compute that? All right. Clear this out here. All right, number 49, throw this in your classwork. A radio DJ is contractually obligated to run a commercial for Pepsi 3 times, a commercial for the local law firm once, and a new promo for the station twice per hour. How many different ways can he do this in 1 hour? How many different unique ways can he do this in 1 hour? All right, go ahead and see how many different arrangements are possible in 1 hour to run these commercials. All right, ladies and gentlemen, there are a total of 6 commercials that have to be run in an hour. 3 Pepsi commercials, 1 for the local law firm, and 2 to promote the station. Okay. So that's a total of 6 commercials per hour. But the Pepsi commercial repeats, the same old Pepsi commercial repeats 3 times. And that's why we got divided by 3 factorial. Local law commercial, or law firm commercial repeats 1 time. And the station promo repeats twice. That's what you have to work out. You know, there's 60 different ways of 60 different or unique ways of running these commercials in 1 hour. Anybody get that there? 60 different ways, unique ways. All righty. Let's see here. It's 18 after. One more. Number 59. The panel for a political forum consists of 4 Democrats, 5 Republicans, and 3 independents. In how many orders can they be seated if all that matters is party affiliation and not the actual individual? All right, that'll be the last classwork, number 51. All right. There's a total of 12 politicians, 4 Democrats plus 5 Republicans plus 3 independents. That's 12. But we have 4 Democrats, 5 Republicans, and 3 independents. So we have to divide 12 factorial by 4 factorial, 4 repeats for Democrats, 5 factorial, 5 repeats for Republicans, and 3 factorial, 3 repeats for independents. You get 27,720 unique or different, okay, political panels that can be formed from these 12 politicians. All right. Okay, so today we accomplished looking at the fundamental principle of counting and also permutations, whether all of our objects are unique or not unique. And this ability to enumerate possible outcomes will enable us to compute more complicated probabilities in the near future. All right, so I will stay on the line. If anybody has any questions or comments, I'll be on the line for the next couple of minutes. And if not, have a safe Halloween.
I had sent you an email like a couple days ago.
All right.
I don't know if
And
you have
who
received
am I
it.
speaking to?
Kenyatta.
Kenyatta?
Yeah.
What's your last name?
EJIJEH.
All right. What's going on now?
Because I was letting you know that I just got back from Canada yesterday, and my internet connection was not great at all.
Yeah.
And I wasn't able to still do my quiz, so I was wondering how I go about that because I think it's closed out now.
Which quiz is that?
Chapter 7.
The Chapter 7 quiz. All right, let me take a look here and see what the schedule has us doing with that. That's due October 29th midnight. Yeah, that was due a couple days ago. Okay, so you need that opened up again, right?
Yeah,
Let me ask you this. Have you ever attempted that quiz yet?
I did, and I had emailed you about it because every question was like loading up